Welcome to Edexcel's M1 June 2003 question 8. Okay, in this question it's all about force, resultant forces, resistance forces, masses and acceleration. Obviously you can put together what we're going to be using. Okay, so we've got this car that's broken down, run out of petrol because the driver has been a complete and utter idiot and not been paying attention to the fuel gauge, or they're an egomaniac where, you know, they're constantly worried about the environment but they'd rather break down and pay something to tow it. Anyway, besides that, the actual mass. Okay, so we've got a mass of a car which is 800 kilograms. The mass of the truck pulling it in support is 1,200 kilograms. The resistance force on the car due to the air resistance, the road, etc. is 400 newtons. The resistance on the truck is 600 newtons, but the truck provides a driving force of 2,400 newtons. Okay, so that's all the information we're given so far. Oh yeah, and this what I've labelled T is this inextendable string. Okay, right. So the first thing we're asked to do is ask the acceleration of the truck and car. Because it's in an extendable string, obviously, because the car's dead, in essence, it's not moving, it's not providing any force, the only force is being provided by this truck. And because the string isn't going to change in length, it'd be logical, therefore, to assume that the acceleration of the whole system is going to be the same. So therefore, we can treat this, because the truck is also having the resistance of itself, plus the resistance of the car pulling it back, because the car's not getting rid of this 400 newtons, it still exists in the system. Okay, so therefore you can assume the total resistance force in the system to be 600 plus 400 newtons, in other words, 1,000 newtons. Good maths. And the total forward force to be 2,400 newtons. The key with this, part A, is to consider the whole system as one object, okay? So we know the total mass, okay, is obviously the mass of the truck, which is 1,200 kilograms, plus the mass of the car, okay, which is 800 kilograms. So obviously, therefore, using advanced maths, that's 2,000 kilograms. Okay. And we know the total resistant force, so the total driving force to be 2,400 newtons. Okay, but there's a total resistance force of 600 newtons plus 400 newtons. So you take that answer away. In other words, you take 1,000 newtons from 2,400, which obviously, therefore, there's the resultant force of 1,400 newtons. Okay, and we've got total mass is 2,000 kilograms, and a total resultant force of 1,400 newtons. Okay, so you just put it into the equation F equals ma, rearrange to get A. So A is the resultant force over the mass. Okay, so therefore, the resultant force is obviously 1,400 newtons over your 2,000 kilograms. Okay, should get you the A acceleration to be 0.7 meters per second squared. Okay, and that's the acceleration of the truck and the car. Now the reason we're not doing it individually is because, well, if we just did it for the truck, we wouldn't be encountering the car, and if we did it for the car, we wouldn't be encountering the truck. I know that might not make some sense, but basically, if we just did the truck, in essence, we did the 600 newtons on the truck and the 2,400 pulling forward, we're not considering the fact that there's a car on there, so the acceleration therefore would be different for the truck and the car, purely because the car doesn't have a forward momentum. Okay, so therefore that's why you would assume that. Try to build it up, but I mean it's more logic than anything else, and if you got it, you got it. If you didn't, weirdly enough, you didn't. Okay, so the next part B, says the tension in the rope. Now the tension in the rope is created because there's a difference in the resultant force of the truck and a difference in the resultant force of the car. Now, the way we do that is by working out, the reason there's a difference is because, well, obviously we've got this 400 newtons pulling it back, okay? Yes, there is a 600 newtons in the truck, and we could work out that and take it away from the car, okay? But basically, if we're looking at the car, so if we just take into account the car, okay, there's a forward force of the T, okay, there's tension. There's also a resultant force pulling it backwards of 400 newtons. We don't need to consider the 600 newtons because we're not looking at the truck. As I said, I'm looking at it from the perspective of the car. Okay, so what force would we? Because the force that's pulling the car forwards is the tension. Okay, so therefore this T is a force, and we take that away from the 400 newtons pulling it backwards to get the total resultant force, and that's equal to the mass of the car, which we know is 800 kilograms, times the acceleration of the car. Now, we just worked out the acceleration of 0.7 meters per second squared, okay? So therefore what we do is we just simply rearrange this, so we work out whatever this is and add 400 to it. So in other words, T is equal to, brackets, 800 kilograms times 0.7 meters per second squared, and we add to that the 400 newtons. Okay, and if you sub that in your calculator, you should get a value for T as 960 newtons. Unless I've read it wrong, in other words, I'm a complete and utter idiot. Anyway, so that's really how far we should have got. Question C. Well, we've got a little bit more of the paragraph. It said the truck and the car are moving at 20 meters per second. When that happens, the rope breaks. Okay. The engine power of the truck. So basically, at 20 meters per second, this truck, the cable snaps. The truck driver goes, stuff your car. We're leaving you behind, and continues off as though nothing's happened about his merry way. Okay. And they accelerates to 28 meters per second. Okay. But there's still a 600 newton resultant force on the truck. Resistance force on the truck. Okay, but basically after 20 meters per second, the truck obviously it's going to accelerate faster. Show that the truck reaches a speed of 28 meters per second approximately 6 seconds earlier than it would if the rope had not broken. So what, in other words, what it's saying is, imagine the rope doesn't break, even though really it kind of wouldn't, hopefully. So work out the difference in the time. So work out the time it takes for the truck to reach 28 meters per second from 20 meters per second, not from 0, remember? Okay, with the car on the rope, and then work out the time it would take if the truck was just to accelerate on its own from 20 meters per second to 28. Okay, so that's really what we're doing here, and it's just to show there's a 6 second difference between them. Obviously, the truck on its own is going to accelerate faster, so there should be a smaller time for the truck on its own. If you don't, then you probably need to redo your maths or get a logic live test, which I probably should come up with, charging people. Anyway, okay, right, so if the first thing I'm going to do is, well, if the rope had broken, what would we have experienced? Now obviously this is going to be the one with the smaller time, okay? So the way we do this is obviously, we work out the acceleration, and then we use simple SUVAT equations to be able to work out the time it would take, and then we don't need to, basically we need to work out the acceleration of just the truck, okay, pulling itself, and we already know the acceleration of it being attached to this car with the rope, because that's what we worked out in part A. There's no need to use resultant force equals mass times acceleration again, unless you want to waste some of your life, then by all means do that, but you know, you're watching my video, so you've probably done enough of that already. Anyway, so the first thing we're going to do is work out the acceleration of just the truck, okay? Because we know the acceleration of the whole system, which we said was this 0.7 meters per second square. Okay, so using the same principles we did for part A, we're just going to apply that, but just looking at the truck, because we're assuming the rope broke, okay? So we can leave the car behind and shove the car off. The people in the car probably die from, you know, certain diseases, but let's forget about them, we're doing physics here. Anyway, so resultant force is equal to mass times acceleration, obviously. And the resultant force, force forward, take the force, so it's just do the 2,400, take the 600 newtons. Okay, so 2,400 newtons, take the 600 newtons, and that's the resultant force, and that's equal to the mass, which we know the truck is just 1,200 kilograms, just times the acceleration. Rearrange that to get the acceleration. Okay, so in other words, the acceleration is equal to 1,800 newtons over 1,200 kilograms. Okay, which should get you 1.5 meters per second squared. Okay, so that's the, but we're not finished, remember, we've got to, so that's the acceleration of the truck without the car. Obviously we assume that to be higher, and that's exactly what we've got, okay? Right, so we know the initial speed, so let's work out the SUVAT equations now. We know the initial speed is not 0 because it's starting at 20 metres per second, and we're working out the time it takes to get to 28 metres per second, so obviously that's the final speed. Okay, we're not really interested in the actual distance it covers. Okay, all we want to know now, sorry, we also know the acceleration, we just worked out 1.5 metres per second squared. What we want to work out is t. Okay, so we've got v, u, a and t. So obviously, I've just kind of said the formula, so obviously we're going to use v equals u plus at. So we can rearrange this to get t. Okay, so a is delta v over t, so therefore t is equal to delta v over a. That's just the way I think about it. You may actually rearrange that correctly, in which case, well done, you're a better person than I am. Okay, so really what it is 28, so t is equal to the change in velocity, which is 8 metres per second, or 28 take 80, sorry, 28 take 20 even, over your acceleration, which we just worked out, 1.5 metres per second. So therefore, if you do that, you will get a time of 5.3 seconds recurring, okay? And therefore we would expect the time of so what you might want to do is put a heading here, you know, time for the truck, just the truck, to get to 28 metres per second. What we need to do now is work out the time it would take for the whole system to get to 28 metres per second from 20. Now there's no need to work out the resultant force. As I said, we've done that before. We worked out the acceleration. So okay, this is the second part. Just going to underline this. Okay, so we know the acceleration. So sorry, we know the initial speed. Sorry, it was 20 metres per second, same as the last one, and the final speed is again 28 metres per second. But the acceleration this time is 0.7 metres per second squared, and again we don't know t. So we just follow the same principle. You can just copy it straight in from below. So therefore t is the change in velocity over the acceleration. Okay, so the change in velocity is still 8 metres per second. Okay, but the acceleration is 0.7 seconds. Okay, so obviously, clearly, this is going to be larger. And it does come out to be around 11.43 seconds. And what you would do there is show that the change in time, okay, so that's seconds, there's a change in time of approximately 6 seconds. So it would take 6 seconds longer for the truck, just the truck, to reach 28 metres per second. Sorry, just the whole system to reach 28 metres per second, as opposed to just the truck. Okay, so that's question 8. Really, it's quite a nice, simple resultant force question. It's just a case about thinking about it. Personally, I would recommend you draw something like that as a diagram. It doesn't ask you to, but it's always nice to see where your resultant forces are coming from. As I said, it's quite a nice one because normally question 8 is something to do with the slope and something quite nasty, but in this case it was quite simple. F equals ma idea. Okay, so thanks for watching, and we'll see you in the next video. We have reached the end of the paper, by the way. There's no more. If you're desperate to find another M1 video, there are other M1 tutorials that I've done. So thanks for watching, and don't forget to do whatever you do, subscribe or whatever it is on these days on YouTube. So thanks for watching, and hopefully we'll, I don't know, do some. Oh wait, shut up. Okay, see you. Bye.